Hello, class. Okay, so we're continuing with our cosmology topic. So today we're going to look at Hubble's constant and the age of the universe. So you did your paper on Hubble. You did a little bit of research on Hubble and how Hubble discovered the red and blue shifts, meaning that objects far away are moving faster than objects that are closer. Everything in general is moving away, but things that are twice as far away have twice the speed, and objects that are 3 times as far away have 3 times the speed, and so on and so on. So whether you saw that in your research or not, what that's called is Hubble's constant. So H. What Hubble's constant basically is, so this is just seconds, it's just the ratio of an object's distance versus the object's speed. So it's a ratio of the object's speed to its distance. Okay, and whenever we measured, and astronomers and scientists and physicists have measured just about every galaxy we could possibly see, and we come up with, and we keep seeing this constant. So it is, that's why it's called a constant. It is constant throughout the universe, no matter which galaxies we look at, based on its ratio of its speed versus its distance, it comes up with about this number. Okay, and also we have what's called Hubble's law. And basically it just puts this into an equation of where this came from. So basically the velocity of a galaxy is equal to Hubble's constant times its distance from us. Okay. Obviously we have to measure it from here because it's the only reference point we have. But because all the galaxies basically share the same constant reference to us, they also share that same constant reference to every other body, because it's constant throughout. That's what a constant is. Okay, so what that means is, so say the universe is this big. Okay, based on Hubble's constant, if we go backwards, we know at some point the universe was this big. Okay? And then if we keep going backwards, the universe gets smaller and smaller until it gets to a point. Okay, that point is the Big Bang. Okay, so basically we don't know what caused the Big Bang. It's most likely due to some gravitational quantum fluctuations that happen within space itself. But what caused those fluctuations, we don't really know yet. There's a lot of crazy outlandish theories out there. Some of them are supported by some evidence, some are not. But that's as far as scientific knowledge goes. That's as far back as we are sure. We know the Big Bang happened. We know it was probably caused by some microscopic fluctuations called quantum fluctuations. But that's pretty much all that we can go back for evidence. Okay. So now moving forward, so if we're here moving forward, we know the universe is continuing to expand, and we know at some point in the past it contracted back to a single point. Okay, so if you remember from physics, back in kinematics, like distance, or the velocity is distance over time. Okay, so the way we calculated the age of the universe, and that's what I'm going to go through here, is how to actually calculate the age of the universe. And it's based off of this data that Hubble and all scientists after Hubble have found of the ratios of distance versus speed. Okay, so to give you an idea of how we do this, so here was the Big Bang. Let's say the Big Bang happened, and out of the Big Bang, 3 objects emerged. Okay, now obviously there was, almost countless objects, but we're just going to pick 3 to keep the calculations simple to show you. Because to do a ratio, all you need is 2. But the more objects you have, obviously the more concrete your math is. So we'll just do 3. So say this is object 1, object 2, and object 3. Okay. So this one travels a distance, d1, and it has a velocity of v1. So that's this distance and this velocity for this object. And this is object 2, so it has its own distance and it has its own velocity. And this is object 3, so it's going to have its own distance and its own velocity. Okay. Now, distance and velocity, remember, were related through time. So all kinematics is based on time. So what time are we talking about here? Well, from the instant the Big Bang happened till now. So basically the age of the universe. So we're going to call T age of the universe. Well, okay, so the age of the universe. So basically, all the objects, they might have their own distance and they might have their own velocity. However, they're all contained within the universe, so they've been traveling for the same amount of time. So that is one thing that is constant. Okay, so the distance is velocity times time. So the distance for this first object is its velocity times the age of the universe. The distance for this second object is its velocity times the age of the universe, because that's how long they've been traveling. And same thing for object 3. Okay, so in general, what we can say is any object's distance is equal to its velocity times the age of the universe. Okay, the age of the universe is distance divided by velocity. So if we know the farthest object and we know its velocity, we could calculate the time it's been traveling, which would be the age of the universe. But also, we can use Hubble's law, because that might be kind of hard to find a distant object, because once you find it, how do you know that that's the farthest object? So basically, we can just use Hubble's law, and we could get all the ratios of all the galaxies, how fast they're traveling, and for what their distance are, and using Hubble's law, we can use that ratio for this calculation. So Hubble's law says that an object's velocity is Hubble's constant times that object's distance. Now for this one, if we solved so notice that the age of the universe, we have d over v. We could do that same thing here. So d over v is equal to 1 over Hubble's constant. Okay, divide by d, and then take the inverse of each side. Okay, so now we have two relations here that are equal. We have dv is equal to 1 over h, and we have the age of the universe is equal to dv. Okay, so what that says is basically that the age of the universe is 1 over Hubble's constant. 1 over Hubble's constant, where Hubble's constant is 3 times 10 to the negative 18. So this is in seconds. Okay, so this is the age of the universe in seconds. If you plug that into your calculator. Now if you want to know it in years, you would convert this to years. So in years, so let me do a quick little math here. Do some conversion. Okay, so if we want to do that in years, so let me show you how I do it in years. So it's just conversion. Like if you wanted to convert seconds to years, you need to know how many seconds are in a year. So 1 year is 3 times 10 to the 7 seconds. Okay, so we can convert that to years. Okay, if you plug that in the calculator correctly, you'll get 10 billion years. And that is the estimated age of the universe. We say 10 billion years just to kind of round it to make it easier. However, just like pi, depending on how many numbers past the decimal you use, same thing for Hubble's constant. Okay, so we know Hubble's constant a little bit more accurately than this actually is. It's like we can go down to many decimal places after this. So if we do that and we calculate it a little bit more accurately, that's where we come up with the 13.4 billion years, just by using a little bit more accurate estimation of Hubble's constant. So that's how we know it's around 10 to 13 billion years old. Okay, so it's actually pretty simple math using basic kinematics and using some simple data that Hubble has started, and we've been recording this data since the 1920s. Okay, so that's the lesson for today. Hopefully you found that a little interesting, and if you ever want to know how we actually calculate the age of the universe, that was how. It was using Hubble's constant. Thanks, guys. Have a good day.